today we are going to start our second part in this course, which is on electronic instruments. So far we have studied mostly classical electromechanical instruments. All instruments that we have studied were electromechanical. There were no electronic circuit at all. There were no digital electronics, neither analog electronics, nothing. Today we are going to start electronic instruments which can be either digital electronics based instrument or analog electronics based instruments. Okay. So, before we go in the core or the heart of this course, this part, we will spend some time in reviewing the required backgrounds, particularly some simple digital electronics and some analog electronics, mainly op amps. So, we will spend significant amount of time in understanding basics of digital electronics and op amps, and then we will dive down into the heart of this course. Okay. So, this is our first chapter today, and in this chapter we will start our discussion from flip-flops, and we will go till the counters. We will develop counters from flip-flops. Okay. So, let us start with what is called an RS flip-flop or SR flip-flop. What is it? So, this is a black box, okay, which has two inputs. We call them set, reset, S and R. S for set, R for reset, and which has one or two outputs. We can call them Q1, Q2, or we can call them Q and Q bar. How does it function? So, the way it functions is that, okay, let me write the rules. Okay, so this is a digital equipment, digital circuit. Therefore, the inputs can be only logical high or logical low, true or false. Okay. So, it cannot be a continuous voltage, it can be only a high or low, it can accept only two values. Okay. Now, the rule is, so that means I can give 4 different choices of inputs, high and high, low and low, high, low, low, high, so on, or 0 1, 0 0 1, 0 1 1, so on. So, I can write the rule as set, reset. So, these two are the inputs and outputs are Q and Q bar. Okay. So, if I give say 1 and 0, the rule says Q will become 1. If I give 0 and 1, Q will become 0. Okay. So, the way it behaves, like if I give, so we call it, you can call that we are pressing the button set. Okay. So, if we press this button set, if set is pressed, Q is set to 1. Okay. So, Q is set to 1. So, here we write Q is set to value 1, and if we press the reset button, okay, by making reset equal to 1 and set equal to 0, this will Q is reset. Reset means is gone back to 0, reset to 0. This is how we call it. Okay. And then what else can we give? We can give 0, 0, and we can also give 1 and 1. What will be the output in these two cases? This case is not allowed. This input is not allowed. What do I mean by that? If you are using this circuit, whatever this flip flop, you are never supposed to give input as 1 and 1. If you give by chance 1 and 1, what its output will be after that, that's unpredictable. Okay? If you give 1 and 1, you are not allowed to give. If you give 1 and 1, we cannot say what is going to happen. So never do that. 0, 0. So if you give 0, 0, what will be the value of Q output? We say that the value of Q will be same as Q previous. That means, what is Q previous? Q previous is the value of Q which was there before you gave this input 0, 0. Okay? So before you gave this input, some value was there. That could be 0, that could be 1. That value will remain. Okay? If the previous value was 0, after you give this input, it will remain 0. If the previous value was 1, it will remain 1. Okay? So this we call, we can say previous value remains, or you call it holding state. So previous value is hold. Okay. So this is how output Q behaves. And what about Q prime? Sorry, Q bar. Q bar, this bar is the symbol for complement or negation. So Q bar will be always opposite to Q. If Q is 1, it will be 0. If this is 0, this will be 1. Okay. So this will be Q previous bar. And yeah, so this is the input output rules, or we call it the truth table. Okay. So this is how this flip flop behaves. Okay. So this is how it behaves from the input output perspective. We haven't said yet what is there inside. That is different question. But from input output behavior, this is how it behaves. So you first know this thing. And then we can talk about what is there inside, internal circuit. Internal circuit is very simple. We basically have, what is this? A NOR gate. This is another NOR gate. Two NOR gates. Each of them will have two inputs and one output. The way we will make the circuit is that we will connect the output of one to the input of other, and similarly the output of other goes to one of the inputs of the first one. Okay. So then there are two more inputs left, and then this we will use as the inputs where we can give some values. So these are the final inputs of the circuit, and these two, okay, are the outputs. And then I seal everything in a box. Then this is same as a SR flip flop. Okay. It has two inputs, it has two outputs. Okay. So, okay, let me call this outputs Q1, Q2, and let me call this S and R. I could have just called this S and this R, no problem, because the circuit is symmetric. So, I can call either of them as set, the other R, no problem. Okay. So, whichever you like you call set, the other one is reset. Now, let us see how it behaves. So, if we give say input 1 0, 1 and 0 here. Now, if this is 1, what will be the value here? This is 1, no matter what the value here is. Okay. So, this part is an OR gate. So, 1 ORed with anything is 1. So, here that means we will at this point we will have 1, and this bubble is a negation complement. So, after this we will have 0. Okay. So, I have 0 here, and then this 0 comes here. So, I have 0, 0 0 ORed 0 or 0 is 0, and after this bubble it is the opposite 1, right. So, I have 0 and 1 here. So, if I give 1 and 0, set 1 reset 0, output is Q1 0, Q2 1. Let me call this Q2 as Q, and let me call this as Q bar. Then you see this rule, come back to this rule, set 1 reset 0 1 0, output is Q1 Q bar 0. Here it is 1, Q1 Q bar 0. Okay, we have got that. So, this is true. Now, let us check the other conditions. Let us make it opposite 0 and 1. So, what will be the output? Okay. So, now similarly this is 1, if this is 1, no matter what this value is, 1 or 1 is of course 1, if this is 1, this is definitely 0, and if this 0 comes here, 0 or 0 is 0 here, after this bubble 1. So, if I give 0 and 1 like this, 0 and 1 here, then the output is Q is equal to 0 like this, Q bar equal to 1 like this. Okay. So, this condition is also satisfied. Now, let us check say other situations. Let me give 0 and 0, and let us assume the value of Q was Q previous before I made this 0 and 0. So, let us start with this. This equal to Q previous, this could be 0 or could be 1. Now, this Q previous comes here. So, here I have Q previous ORed with 0, something ORed with 0, something plus 0 is something, that something. So, at this point we have Q previous, and then at this point after the bubble we will have Q previous bar. Now, this Q previous bar comes here. Now, this thing plus 0 is of course this thing only. So, Q previous bar, and after this bubble this bar will be gone, I will have Q previous. So, you see I started with the assumption that this is equal to Q previous, and I landed up with the fact that this stays with at the same value Q previous. This value is not going to change. As long as you keep this 0 and 0, this value is not going to change. So, this is a holding state. This is also true for this circuit. Now, if you give 1 and 1, what will happen? I keep it as a homework. You think yourself, it will be fun. Okay? If you think something yourself, this will be more fun than I myself telling you everything. So, homework, think what happens if S equal to 1 and R is equal to 1, which is not allowed. Okay, great. So, this is all about SR flip flop. Now, so what do we see? We see that there is a risk. Okay. So, there is a risk that one may accidentally make both this set and reset equal to 1. There is a risk of accidentally, say, making set equal to 1 and reset equal to 1. That means, I say there is a chance of pressing set and reset simultaneously, which is not allowed. Okay. So, this circuit has some problem. When it comes to practical use, this is a risk. So, therefore, we are going to see a modification. What is that modification? The modification is simple. So, let me first draw the SR flip flop. Input goes to output, output goes to input. Now, what I will do, I will connect, say, a NOT gate. So, this is a NOT gate. Okay, or I can also connect it this here, both will be same. So, either here I connect a NOT gate or here I connect a NOT gate, and then I sort these two, and this is my input. Okay. So, this was S, this was R in the SR flip flop, this was Q, this was Q bar in the previous diagram. Now, I have made this modification. Instead of allowing two inputs, I allow only one input, and this input goes both to set as well as reset, but I have a NOT gate in one of the paths. So, therefore, whatever this value is of course always opposite. If I give a 1 here, then I will have 1 here and 0 here, but if I give, say, a 0 here, I will have 0 here and 1 here. So, this ensures that set and reset can never be equal to 1 together. Okay. So, therefore, now S equal to 1, S equal to R equal to 1 is not possible. Since we have only one input. Connected in this way. Okay. So, that risk is gone. But now, there is a problem, another problem. What is that another problem? We cannot even have S equal to R equal to 0, because S equal to R is never possible in this circuit, they are always opposite. So, this S equal to R equal to 0, that is not also possible, but this is a valid state. Okay. So, but this is a valid input. Okay. So, we will also lose that possibility. So, that means holding not possible, holding not possible. So, what can we do? What we do is this: further modify this. Copy paste. Now I will put two AND gates. So this is a AND gate. It has two inputs. So this is AND, and here also I put another AND gate. And I connect these two. Okay, so this has two inputs, this has two inputs. I connect one of their inputs together and I bring this out as another input. So these two are now two inputs. Okay, so let me call one as D, another as E or En. This En now stands for enable. What does it do? If enable is 0, let's see, if En is equal to 0, then what happens? This 0 goes here and here. Now no matter what this value is and this value is, that means no matter whatever the value of D is, I will have 0 and 0 here. Okay, at set and reset. This is set, this is reset. Okay, so I will have 0 and 0 at both set and reset. So this is now the holding state. So I can give this equal to 0. Okay, so if I make this equal to 0, now no matter what the value of D is, this flip flop, SR flip flop, will be in 0 0 input. That means it will hold the previous value of Q and Q bar. And if enable is equal to 1, then this is D. This D goes here, this is equal to 1. Now 1 and D, so this is D, and here I have D bar. So D and 1 is of course D. Okay, D and 1 is D. So S will become D and R will become D bar dot 1 is D bar. Okay. So that means if D is equal to 1 with enable equal to 1, then S is 1, R equal to 0. So this will set Q to 1, Q will be set to 1, and if D is equal to 0, then so Q will become 0 or reset to 0. Q will get reset to 0. So from this two you observe when enable is equal to 1, Q is equal to D. Isn't it? When enable is equal to 1, then if D equal to 1, Q becomes 1. If D equal to 0, Q becomes 0. So in this circuit, you observe once again that if enable equal to 1, then Q equal to 0. Sorry, Q equal to D. Whatever the value is D of D is. If D is 0, Q becomes 0. If D is 1, Q becomes 1. And when enable is equal to 0, then Q stays at Q previous. So this is the rule of this new circuit. Okay, this new circuit has this rule, and then we give it a name. We call it data flip flop. Why do we call it data flip flop or D flip flop? D for D or data flip flop. And that is why I actually called this input as D. Okay. So, let me make a box. So, it has two inputs and it has one or two outputs. I do not need Q bar outside because Q bar is always opposite to Q. This is redundant. If you want, you can take it outside, no problem. So, this has two inputs, one output, and the rule is that, and the rule of this circuit, let me write, oh, it's here, it's already here. If you make enable 1, then output will become equal to input, and if enable is 0, then no matter whatever the value of input is, data is, output is not going to change. So, this is called a data flip flop because it can store one bit of data. How? By giving a number 1 or 0 here, we can get that number copied at the output. We also have to make enable 1. So, if enable is 1, this data, this input data is copied at the output, and then if we make this enable 0, then this previous value of that data remains. It stays, it is never changed. So, it memorizes that value. That is why we call that this is a memory element. This stores the data that comes here when the enable is on. So, let me just write a few words. Okay. So, this D flip flop memorizes the value of the input D when enable is equal to 1 or enabled, and then it keeps it as long as enable is equal to 0. Okay. So, if you keep the enable equal to 0, as long as you keep enable equal to 0, if you change the value of D input, output is not going to change. Okay, good. So, now next we are going to see another flip flop. Okay, so before that, the above D flip flop or data flip flop is called an level triggered or level enabled flip flop. Why? Because input is copied to output when enable is at level 1, level high, and output does not change when enable is at level 0, no matter what the value of D is. So, this is sensitive to the level, whether the level is 1 or 0. Okay. Now, what we want, so this is next thing what we want. So, now what we want is that the input is copied to output, that means D is copied to Q at a particular instant whenever we want. Okay. So, this is like the situation is like this. Say this is, let me draw some timing diagrams. So, this is time t, and say this is the value of d, it is changing. This is d, which is changing with time, and say we have time versus enable. So, this is E n, and say this enable is changing like this. This is changing. So, this is 1, this is 0, here this is also 1, this height is 0. Now, what we want the Q, which is the output, to change, say only at the instant when enable goes from 0 to 1. So, this is a rising edge, this is a falling edge. Now, we want that the output, the input should get copied to output only during the rising edges of this enable signal. So, this is a small instant, okay? This is a very small instant of time. So, we want at this point Q should become equal to the D. Now, at this point D is equal to 1. So, Q will become 1 here at this moment. So, Q will become 1 at this moment. We do not know what the value of Q was before this. It could be 0 or 1, we do not know, but at this moment it should become 1, because at this moment D is equal to 1. And then after that the enable signal is constant. So, we want the output not to change. Here there is a falling edge, we want the output not to change even during the falling edge. Then this is again constant, we want output not to change. So, that means from here to here the output will remain unchanged to this value of 1. And again we have here a rising edge. So, at this moment once again the output can change. And how will it change? It will become equal to the value of D at this moment, and at this moment the value of D is equal to 0. So, now the value of Q should go to 0, and then it should remain unchanged as long as this is constant, or as long as the next rising edge does not come. This is what we want, and this is what we call as edge triggering. Okay. Why edge triggering? Because this is triggered, this change of the output is triggered only at the edge. To be more precise, we call it the positive edge triggering, because this is triggered only during the positive or rising edge. It is not triggered during the negative or falling edge. So, this is rising or positive edge. So, that is why we call this positive edge triggering. Okay. Now, in comparison to the previous situation, okay, so let me copy it. So, this is what we want now. And now, let us see what we had before. This is what we had before in this circuit, okay, and this is a level triggered D flip flop. What happens in this circuit? Let us see that. Let us take the same input D and same input enable. So, let us see how the output will change in this case. This is level triggering or level triggered D flip flop. Okay, D flip flop. This is also D flip flop. So, in this case what will happen is this: the portion where this enable is 1, that means from here to here the output will be same as the input. So, here the output will be 1 because input is 1, then here the output will be 0 because input is 0, and then up to this point it will remain 0, then it will become 1 again, and then it stays 1 like this, then here it becomes 0 again, up to this it is 0, okay, fine, and then the enable is off. So, here to here no change will occur. So, this will remain like this up to this. Then here again enable is 1, so output can change, but it will not, it can change, but D is also 0. So, up to this will remain 0, here it will become 1, here it goes to 0. So, now it will copy the same value as long as enable is equal to 1. So, this is level triggered D flip flop. This is what we have seen so far, and this is what we now want. Next thing what we want is this. We haven't seen this circuit yet, but this is what we want. We are going to see this. We are going to make this circuit. Okay. So, before that, let me tell you the symbols. So, if I draw a box with D means data input, Q output, enable, this is also an input like this. This symbol is for level triggered D flip flop or data flip flop. But if I draw the same thing, D Q as here, but if I put a triangle and I write enable, then this triangle symbol means this is a level triggered D flip flop, sorry, edge triggered D flip flop. I can also sometimes draw it this way, where I will have a small bubble before this. This is also edge triggered D flip flop, but there is a difference. What is the difference? This is positive edge triggered flip flop and this is negative edge triggered D flip flop. That means, what does that mean? That means this is positive edge triggered D flip flop, what we have already seen, and What happens in case of a negative edge triggered? The only difference is that the changes occur only during the negative edge, not here. Okay. So, the changes occur only during the negative edge. So, what will happen? Here q will become 0 at this instant, because data is 0. So, q will become 0 and it will remain 0 until and unless we get another negative edge, maybe much later, maybe here where this is 1. So, here it will become 1. Before this we do not know what the value is. Before this, whatever the value was, it was there, we do not know. Okay. So, this is the symbol. Now, let us make the circuit. Okay. So, circuit, so the next thing we will study is the circuit of a edge triggered D flip flop. And this particular circuit is called a master slave circuit. This is the name. We will understand soon why it is called so. So, what we will do is this: we will take two D flip flops, two level triggered D flip flops. So, let me just take this. One, two. Now, what we will do is this: we will connect the output of the first one to the input of the second one, okay? And so you can call this D1, Q1, D2, Q2, and then this input will be the main input. Okay. So, I am going to make a level triggered circuit with this, sorry, I am going to make a edge triggered circuit with two level triggered D flip flop. So, this two together will be my edge triggered circuit. So, the output of the first one goes to the input of the second one, and this input is the main input. You can call it the D, same as D1, and this will be the final output or main output. You call it Q, which is same as Q2. And this to enable, what I will do is I will connect them together via maybe a NOT gate. So, I can put the NOT gate here and take the input like this. I will call this enable En, call it En1, call it En2, or I can also do it this way. I connect it here and put the inverter here, the NOT gate here. So, this is a NOT gate. Both will work. One of them will work as a positive edge triggered circuit, another will work as a negative edge triggered circuit. Let us see how this one works. Okay. So, what I will do, I will draw once again some timing diagrams. Okay. So, let me first draw enable. Okay. Say maybe this is like this. Then I can draw enable 1 and enable 2. Okay. Enable 1. So, I just write En is equal to En1, correct, because sorry, En is equal to En2, because enable goes directly to enable 2. Okay. So, I do not have to draw it separately. Now, let me draw enable 1. Enable 1 is nothing but the negative of enable 2 or enable. So, 1 here, 0 here, and like this. Now, when enable is is 1, say 0. Okay, let me start from here. And let me call this as flip flop 1 and flip flop 2, FF1 and FF2. Here I can write FF1 is off and FF2 is on, right, because enable 2 is on. Here I write FF1 on and FF2 is off up to this instant. Okay. Then once again I can write FF1 off, FF2 on. Now, if FF2, if FF1 is off, first flip flop is off, this flip flop is off, then whatever the value of D comes here will not go to this Q1. Okay. So, therefore, here I can write Q1 will be equal to Q1 previous, right, because D this is not transparent, D cannot go to Q1 because this is off, FF1 is off. So, Q1 will remain as its previous value, whatever the value was before this instant, that value of Q1 will remain here. Now, if Q1 remains at its previous value, what will be Q2? Q2 will definitely be equal. Now, Q2 will be equal to D2. Q2 will be D2 because this flip flop is on. Flip flop 2 is on. So, Q2 is equal to D2. If D2 changes, Q2 will also change continuously. Okay. Q2 is equal to D2 and this D2 is equal to Q1. But Q1 is not changing. Q1 is constant at Q previous at this instant. So, therefore, Q2 here will remain at the value of Q previous. Okay. Q1 previous. What is Q1 previous? Q1 previous is the value of Q1 before this instant. Okay. So, that means we write here Q2 is not changing and it is constant to the value of Q1 previous. Now, let us see what happens here. Here flip flop 1 is on, flip flop 1 is on means Q1 is equal to D1, D1 is equal to D. Okay. And what about Q2? Q2 will stay at Q2 previous. Because flip flop 2 is off. What is Q2 previous? Q2 previous is the value of Q2 before this region, that means here, okay, at this instant, before this region. And what was that value? Q2 was, so from here we see Q2 previous was Q1 previous. So this is equal to Q1 previous, which was the value of Q1 at this instant. Okay, so Q1 previous is the value of Q1 at this instant. So let me draw the value of Q1 and Q2 as well. T, here I draw Q1 and Q2. Okay, now Q1, I do not know what the value of Q1 was. So before this instant, so let me just before this instant call this value, whatever that is. It can be 0, it can be 1, I do not know. I'm just calling it Q1 previous. This value, just before this instant. Okay, so this value of Q1, this can be 0, this can be 1. This value of Q1 will remain here up constant. Okay, and then Q1 can change depending on the value of D. But what about Q2? Q2 is Q1 previous here. So this is equal to Q1 previous. And here also this is equal to Q1 previous. Okay, up to this moment. So up to this moment, this is constant. It's not changing. Okay, now after this, what happens? Okay, once again, let's analyze this part. Okay, so here I can safely write by copying this, Q1 is equal to Q1 previous, which now means is the value of Q1 just before this instant, which is here. What could be that value? That will depend on the value of D. So I have to draw D as well. So let this be the D, and say the value is like this. I do not know. Okay, so then at this instant, D is 0. So Q1, so here to here, Q1 is equal to D. Here Q1 is equal to D. So let me just copy this pattern. So 0, then 1, then 0, then this thing, then 0. Okay, so that means here at this instant it is 0. So then this value is the value of Q1 previous. Okay, I request you do this analysis yourself. Okay, because otherwise it may be a bit clumsy. It's very difficult to make you understand if you do not try it yourselves. Okay, so this value I'm saying is the Q1 previous. No, so now this is in this case equal to 0. So this will be 0. Q2 is equal to, I'm just copying from this because this state and this state are similar. So Q2 is equal to Q1 equal to Q1 previous. Okay, so Q2 will be this equal to 0. So Q2, now you observe with all this analysis, so with all this observe Q2 is changed when when enable goes from negative to positive at this instant. Okay. So, at this instant follow the pointer. Okay. So, at this let me show you this. So, at this instant, okay. So, at this instant q 2 is changed, q 2 which is same as q, that is the output is changed at the rising edge of the enable, okay, and q is not changed, q is, that means q 2 is not changed when say enable is constant equal to 1 or equal to 0, or even when there is a falling edge. Okay. q 2 is not changed when enable is constant or there is a falling edge, negative edge at enable. Okay. So, it changes only at the rising edge and it does not change at the falling edge, and the value of q or q 2 is same as what? It is the value of q 1 previous. Q 1 previous is the value of d just before this instant, this rising edge. So, this is the value of q 2 is same as the value of d just before the rising edge at enable. So, in summary, this value of d is copied to the q. From d to q, it is copied only during the rising edge of this enable signal. So, therefore, this circuit behaves like a rising edge sensitive, positive edge sensitive D flip flop. Okay. So, you can just to denote it, you may just this is, so this you can denote with this symbol. So, what we have made is a rising edge sensitive a rising edge triggered D flip flop. Okay. So, let me just tell the story in a different way. So, I told you the story with timing diagram. Okay. This is one way to verify that this is a edge sensitive edge triggered diagram. Another way of understanding the story is this. So, observe that when enable is equal to 0, okay, then flip flop 2 is off, that means non transparent, but FF 1 is on. So, D data is continuously copied, continuously being copied, present continuous tense, continuously being copied to Q 1. This is a temporary or intermediate stage, intermediate value. Okay. But the moment enable becomes 1 from 0, flip flop 2 is on. Therefore, the value of Q 1, therefore, Q 1 which is same as D 2 is copied. Therefore, the value of Q1 same as D2 at that moment is copied to the output Q. Okay. So, the moment this second flip flop is turned on, the value of Q1 goes from here to here. Okay. And this value, that value, so the value at that moment is nothing but, let me write it in a different color, same as the value of D just before that moment. Okay, because D was being copied from here to here, this was on, D was coming from here to here, and it was getting stored temporarily here. It was not, the second one was not transparent. So, the second one was holding the previous value, but the moment the second one is turned on, the last value of D goes through D2 to Q2. Okay, this is how it works. So, therefore, if we had the NOT gate before say FF2 flip flop 2, that means here instead of flip flop 1, this will behave oppositely like a negative edge triggered D flip flop. Okay. So, this is a positive edge triggered. If we keep this connected directly and put the NOT gate here, then that will behave like a negative edge trigger. Thank you.